let's prove the p-series, which states that the infinite sum to infinity of 1 over n to the p converges if p is greater than 1 and diverges if p is less than or equal to 1. Now, we already showed that the sum of 1 over n diverged, but we'll include it again for completeness' sake. We're going to use the integral test to prove this for p greater than 0. For p less than or equal to 0, we're actually going to use the test for divergence. If you think about it, it should be relatively straightforward. We actually can't use the integral test because the terms aren't decreasing. Okay? So, for starters, let p be greater than 0. Then, I guess we could just say the function f defined by f of x equals 1 over x to the p. Remember, we switch n's to x's, right? We call it a function f of x, right? Is clearly, I think it's pretty clear, positive continuous and decreasing. Again, this is true only when p is greater than 0. So you can think about why that's not true when p equals 0 or is less than 0. Okay? So use the integral test, right? We already stated that up here. Okay? So what we're going to have is, I guess we'll say first for p equals 1, we have the following, right? The limit as t approaches infinity of the integral from 1 to t of integral of 1x dx, and this equals, right, the limit as t approaches infinity. This is, of course, going to be ln of x from 1 to t. And this, of course, is ln of t minus ln of 1, which, of course, is 0. We know that, right? And you can just write, if you want, that this equals infinity. So the sum from, again, it could be from 1 to infinity. But really the important thing is that it's just an infinite sum. This guy diverges, right? So this guy diverges, okay? So we'll say, now, let p be greater than 0 and not equal 1. Okay, so we're not considering the special case where we have ln for integral, right? Now when we integrate, we're going to have, we're going to use a reverse power rule, right? So we have the following, right? Again, limit as t approaches infinity of our integral from 1 to t of 1 over x to the p dx. It might be easier, by the way, just to write this as the integral of x to the negative p. So then when you anti-differentiate, right, it's clear that it's going to be 1 minus p. So this is going to wind up being, I'm not going to write that just for space constraints, but we're going to wind up having x to the 1 minus p divided by 1 minus p. Right, again, this is 1 over x to the p is the same as x to the negative p. Okay, we're over here. We plug stuff in. Let's see what happens. We get t to the 1 minus p, 1 minus p, minus 1 to the 1 minus p over 1 minus p. All right, now let's think about what happens here. If p is greater than 1, then 1 minus p is less than 0, right? So it's best to think of this as the limit as t approaches infinity of 1 over 1 minus p t to the p minus 1, right? We flip the exponent because we're putting it in the denominator, minus, and then this is just 1 over 1 minus p, which equals negative 1 over 1 minus p, or 1 over p minus 1 if you prefer. So our sum converges. Okay. On the other hand, for, I guess we have to restrict p to be between 0 and 1. I'll just point out that 1 minus p is actually greater than 0. So it makes more sense, just sort of intuitively, I'd say, to keep the t to the 1 minus p up in the numerator. I mean, you can write it however you want, but I think it's just better to look at it that way. And this, right, again, you've got a thing in the numerator, gets bigger and bigger and bigger. Doesn't matter how small the power is that it's raised to, it's a positive power. It's going to blow up. Just to highlight this, right? Literally highlight it. That's how we're getting it. Okay? So, this infinite sum diverges. Okay, last but not least, we need to consider the case where p is less than or equal to 0. So we're going to use the test for divergence. Right? Now, I guess technically speaking, we do have a special case. If p equals 0, then our term is just 1, and the sequence converges to 1. But in either case, just to save a little bit of space, so we'll say since the limit as n approaches infinity of 1 over n to the p, which is probably better viewed as the limit as n approaches infinity of n to the negative p, which again, p is greater than or equal to 0. So this is going to equal, well, 1 or infinity, but not 0. I guess we should say the sum from 1 to infinity of 1 over n to the p diverges. Okay? So we've shown that for p greater than 1, series converges. For p less than 1, it diverges. And I guess we also showed that for p equal to 1, it diverges. Okay? So that is the proof of the p-series.